Hi class, this video is going to cover generalizations and predictions and causal inferences. We're going to spend the most time on generalizations because there's a little more nuance involved in their evaluation, and so they don't tend to be as general and familiar in some ways as the other two. So first we need to disambiguate. Yes, that's a word. We need to disambiguate when you say generalization as a statement or as an argument. But a generalization as a statement is just a claim about how many people have a property. So when we say generalization as an argument, we are either concluding one of those statements, that is, concluding that some group has a property, or we are actually using that claim as a premise to make an inference about an individual. So very roughly speaking, generalizations are going to go whole to sample or sample to whole. If we start with a claim about how many people have how many of a group have a property to an individual, that's sometimes called a statistical generalization. So 75% of Americans are under 6 feet tall. Therefore, the next person who walks into the room will be under 6 feet tall. Might be a statistical generalization where we're going from the statistic to the individual. And then the much more interesting ones are called inductive generalizations, where we go from a sample to the generalization. That's an inductive generalization. So notice I've already used the terminology a few times. We use sample and population, right? So the population is the group, the sample is the individual or individuals. Generally, samples, when we're going inductive generalization, samples are the ones that are known to have the property, a little bit like primary analogs. So that's it. That's the whole shebang of how generalizations go. We're obviously going to say a lot more when it comes to evaluation, but the inference simply is, again, in inductive generalizations, we have some sample, so we generalize to the group. So, as Robinson rightly points out, this is a very common form of reasoning. We do it all the time, and our goal in critical thinking is to do it well. So think of some generalizations you might have made, say, from watching the first lecture video or 2 lecture videos, or generalizations you made about online courses generally, or professors generally, or classes generally. Those are all generalizations you've made from your experience, which counts as your sampling. And so this is a type of reasoning we do all the time. So how do we do it well? Pretty much the entire evaluation of inductive generalization, of going sample to whole, all that's required to make it good, to make it strong, is that the sample is representative. That's, roughly speaking, the sample's good enough to let you extrapolate. Now, there's, roughly speaking, 3 ways that could go bad. So how do we get a sample that's representative is our question. If we do that right, we have a strong argument. If we do that wrong, we have a fallacy. So once more, we are going to introduce the fallacies as we talk about how these arguments go right and go wrong. But again, remember, fallacies aren't problems of false premises. It's about the inference. So saying the sample is X is our factual claim. Whether X actually supports the inference or not is the inferential claim, and that's where these fallacies come up. So it ought not go without saying, let's be explicit about it, the first and foremost issue of sampling is the size. And this is where it's important to remember that inductive arguments admit to degrees of strength, because larger samples are better. If you're wondering, you could theoretically have a sample size of 99% of the population and only generalize about the last part. That's a really big sample. But if you've ever watched election night coverage and you're saying, well, how do they project a state to win based on only 10% of the vote being in? It's, well, 10% of the vote is seems small when you're giving it as a percentage, but when you're talking about 10% of the population of California, that's a huge number. And you would have to see some very crazy sampling in order for that to not be representative of the whole. So just sheer size is important. And depending on the kind of generalization we do, depending on our margin of error, depending on how much confidence we need, well, all of those go into it. So again, bigger makes stronger. Well, if we need to be 70% sure of something, that's very different than if we need to be 99% sure, say in calling election coverage. But yeah, bigger is better. So what happens when we don't have a big enough sample size? That is a fallacy called hasty generalization. Definition of hasty generalization: you are simply generalizing on too small a sample. Unfortunately, that's how a lot of stereotyping comes up, is that you encounter an individual or a few individuals and you assume they're all like them. A lot of my family is Chinese, and we you see that a lot. There are 1.3 billion Chinese people. And so to say all Chinese people are like X based on your encounter of 2 to 3 is a really bad argument. It's a hasty generalization. But there's other ways that that could go wrong too, because another issue is you have to have a sufficiently diverse population. Ideally, you want random samplings. So, for instance, the very fact that you are generalizing based on, say, the X number of Chinese people you know, well, the very fact that you know them and you're living in the US means they have certain things in common, right? They're probably educated enough to have applied for certain types of visas if you're encountering them in a professional field, or at least you could say things about the steps they're willing to do to try to improve their lives. That might not be a representative sample. You're picking a subgroup of people who have done all of these things in common. And so when you do that in a way that impedes the quality of the sample, that is, when you don't get a good sample because your method of selection requires these certain commonalities that might impact the conclusion, that is called a biased generalization. Let me give a few more maybe straightforwardly obvious ones if you're unfamiliar with contemporary trends in terms of immigration. Think of when Fox News or MSNBC does a survey. Well, they'll post the results, but you'll see that you'll see some trends of bias there, because say if you're watching Fox News, well, the vast majority of Fox News watchers identify as conservative and are much more likely to support certain things. And so if Fox News puts up a thing that says 79% of those surveyed support this policy, well, that's not 79% of Americans, that's 79% of Fox News viewers, which we have reason to think is not representative. Or I think it was Dowden gave the example of, if you're trying to generalize about traffic patterns and you do it during rush hour, or if you're trying to generalize about students and you're doing it with the honors class, or et cetera, et cetera. There's articulatable reasons why we would think that the sample is not going to be representative of the whole. So if I am generalizing about the height of students at the school, and for some weird reason, most of the basketball team took my class. That would be a non-random sample. And so non-random usually means biased. Uh, it only doesn't when the non-randomness involved is irrelevant. So there's one extra fallacy involved, and neither book mentioned this, but it's a very important one. You can also deliberately create a bias sample. So this is a fallacy where there is intent to deceive. So you select the sample based on the conclusion you want to generalize. When you do that, it is called cherry picking. You cherry pick the data to choose what supports your conclusion. An egregious case of this I saw was about, it was put forward by someone advocating that gun control doesn't work. And they said, look, the murder rates in London, which have very strict gun laws, are the same as Chicago, and they gave data. The data was for like 1 week in a like 6-year period, and that was the one and only week where London had a higher murder rate. And then if you look at the rest of the data, it was Chicago had higher all the way across, or maybe it was New York. Sorry. Anyway, it was very clearly the deliberate attempt to create this kind of bias. And so when you are intentionally misrepresenting the data by presenting true, they're true samples, they're not making it up, but they are selecting deliberately the samples that are getting to what they want to say about the population. That's called cherry picking. And very, very, very common in politics on both sides of the aisle. Uh, so just think of, well, somebody who wants to say something about all conservatives, and then shows shows the following quotes from Marjorie Taylor Greene. Well, that seems to be trying to, and what they're trying to say is negative, and so that seems to be a way to select to get to their conclusion. So that's just bad reasoning. Um, we haven't said enough about it this semester, but just in general, if you have to cheat to win the argument, you're not critical thinking. You're not interested in the pursuit of truth. You're just participating in rhetoric, and that's not what we're doing in this course, and that's not what you should be doing in life. So if your conclusion is the correct one, then give a good argument to do it. If you have to cheat, that usually means your conclusion isn't right. And so, yeah, follow good reasoning where it goes. So don't cherry pick. Don't do any. Try very hard to avoid any fallacy, but certainly the intentional ones. All right, that's what I wanted to say about generalization. Predictions and causal inferences will go a little faster because they're a little less involved and you're a little more familiar. So predictions go from the past to the future or present. But that's not enough. I want to be clear here. That's what they conclude, but what makes it a prediction is how do we get there? What's the inference? And the inference of a prediction, always, what justifies the prediction is that the future will resemble the past. Uh, that's the core of the prediction. So if you're just saying, well, team A is going to win the basketball game, and the basketball game hasn't happened yet, and you're basing it on who's sick that day and who's playing and da 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 da, that's not actually a prediction in the sense that we're using it as an argument form here. The argument form we are using must be the future will resemble the past. So if I'm predicting that the sun will rise tomorrow based on the fact that it's risen every day for the past 2.3 billion years, that's a prediction. So other things might be generalizations in disguise or analogies in disguise and things like that. So the prediction only says the future will resemble the past as your inference, as the way to generate the prediction you make. Um, when do those go wrong is what I've already told you, basically, that, well, if you call it a prediction and you're actually doing things that are dissimilar, like different players playing, or different day, or different venue, then you have to go you do analogical reasoning. And so if you're just trying to make it as a prediction, you're actually doing a bad analogy rather than a bad prediction. But there is one other fallacy to be aware of with predictions, though. It is another false cause. So remember, false causes are where various types of causal inference go bad. I mentioned it's a whole family. One that comes up sometimes, and it's just one to be aware of, is another Latin phrase, sorry, post hoc ergo propter hoc. Post hoc ergo propter hoc. Latin translates after this, therefore because of this. It's actually about explanation. I just thought it would be an okay fit here. The fallacy of this particular type of false cause is because one thing precedes another thing. They think that the bad inference is the thing that precedes causes the other thing. That's why it's a type of false cause. So think of a lot of superstitions. Well, I wore these socks and we won. Therefore, I'll wear these socks again and we'll win again. It's assuming there's some sort of causal relationship that because the one happened first, the other happened second. That is the false cause of post hoc ergo propter hoc. Another one, sadly, that comes up a lot has to do with this um, bad reasoning that vaccines cause autism. The test for autism happens just on a timeline for children. You can't test for autism under a certain age. And so the test for autism happens after, entirely coincidentally, a certain round of vaccinations, because that also has to happen on a timeline to keep a child healthy. And so some people have seen data that says, "Oh, look, all these autism cases happen after the vaccine," and therefore assume a causal relationship, when in fact it's just a measuring issue. Well, you measure or test for autism at a certain time, and that time happens to be after a certain round of vaccinations has caused a bunch of people to endanger their children. So watch for the fallacy of post hoc ergo propter. Post hoc ergo propter hoc. Just because B follows A does not mean that A caused B. Well, how do we fix that, by the way? We start doing uh, generalizations, and we start doing uh, analogies, and we look at different data. We increase our sample, and you say, wait a minute, these people are being testing positive for autism who weren't vaccinated, and it's still occurs at the same time, things like that. And so, by the way, that's not the only fallacy of vaccines and autism. There was also some intentional manipulation of data, cherry picking. So yeah, this is one of the reasons we learn fallacies, because they're dangerous. People get killed because of people falling for fallacies. All right, the last one that I mentioned I would talk about on this video is a very, very, very general kind of catch-all called causal inference. Remember, I described this before as you see the effect and infer the cause, or you see the cause and infer the effect. We already talked about the former because that's inference to the best explanation, where we go from effect to an inferred cause. Uh, how do we deal with the rest? Again, this is a very, very general term. So when we are saying, here's a cause, how do we infer the effect? The answer is actually the other types of argument we've already talked about. We can do analogies to say, well, a similar cause will yield a similar effect. Or we could do a generalization of, well, in this part of the population, X was the effect. So in another member of the population, X will also be the effect. What you're noticing, I hope, is I'm being repetitive. That when we're just going cause to effect, that's just a really, really, really general term. And there's not a whole lot of extra that we need to add here because it's actually covered and subsumed by these other arguments. So we usually reserve causal inference, as I said, as a catch-all. If you're going from cause to effect, but you don't have similarities you could draw an analogy to well, you don't have a prediction where you've seen it in the past, so you'll see it again in the future, or you don't have a generalization where you don't have a sample to infer an effect. So we just use a general catch-all. We'll talk a little bit more about how to refine those later in the course. So that's all I wanted to say about it now. There is one more associated fallacy we should be aware of called a slippery slope, where the problem isn't one cause and effect, it's a chain of cause and effects. So you, if I say, well, A might cause B, so B might cause C, so C might cause D, so D might cause E, therefore A might cause E. When you actually stack them up like that, you go from something that's probable, if it's probable that A causes B, to something that's improbable that A causes E. I could show that mathematically if you'd really like. If A causing B was 70% chance, and B causing C was 70% chance, and C causing D was 70% chance, the chance of A causing D, you multiply them, which means the chance of A causing D is actually 34.3%. Notice we went from something probable, a single link in the chain is probable, but when you stack them up, you don't. That's called a slippery slope. Let's give a more concrete example so you know a little more what I'm talking about. Well, if I fail this exam, I'll fail the course. But if I fail the course, I'll lose my scholarship. But if I lose my scholarship, I'll drop out of college. And if I drop out of college, I'll have to go to the University of Phoenix online. Therefore, if I fail this exam, I'll have to go to the University of Phoenix online. The fallacy here isn't the first cause inferring effect, and it isn't the second cause inferring effect, and it isn't the third cause inferring effect. It's stacking them all up without realizing that you lose probability for each one you stack. And so that's called a slippery slope. Otherwise, that's all we wanted to cover for today, and we're going to hopefully engage in them very closely and deeply and well this week in the discussion boards, and we will see you next time.